Hello everybody and welcome to the 12th lecture of MHM 42780 MUA 781. During the last couple of months or weeks we talked about fundamentals of thermal radiation and radiation heat transfer. We recently finished study team 2, which was focused on boiling and condensation. And today we are going to start with study team 4, which is fundamental of mass transfer. So you might say that, okay, why we are not continuing with the study team 3 and after that the study team 4? The reason for it is that mass transfer is a new concept for you. And we are going to go a little bit slower compared to the rest of the study teams to allow you to understand it better. And at the same time, because when we are done with this fundamental of mass transfer, MUA 781 students will leave us and will join Prof. Slaber for the rest of the course. And beside that, I'm sure the majority of you familiar with heat exchangers, so I decided to move it to the last section while it's maybe during the time that it's more stressful for you, preparation for the final exam, and it's better not to start a complicated subject or a study team at the end of the semester when you are a little bit tired and you want to write the final exam and go and rest. So that's the reason we are going to start with the study team 4, fundamental of mass transfer, and after that we are going to go back to study team 3, which is heat exchangers. So in this study team we are going to speak about analogy between heat and mass transfer. We are going to speak about mass diffusion, steady mass diffusion through a wall, transient mass diffusion, diffusion in a moving medium, and we are going to talk about mass convection. But what's the objective of this study team? At the end of this study team, we are expecting you to understand the concentration gradient and the physical mechanism of mass transfer, why mass transfer happens. You also need to be able to recognize the analogy between heat and mass transfer. You also need to know that there are different ways of describing the concentration, mass base, molar base. We are going to talk about it, don't worry. And relate the rate of diffusion to the concentration gradient. You should also be able to calculate the rate of mass diffusion through a layer, like under a steady condition, predict the migration of water vapor in building, perform a transient mass diffusion analysis. Very simple equation, that's not a big deal. Calculate the mass transfer by convection, and at the end, which is a very complicated subject from my perspective, it's simultaneous heat and mass transfer. That basically adds up the knowledge of mass transfer to the heat transfer that you already learned. We know that heat is transfer if there is a temperature difference in a medium. So we can say that the driving force of heat transfer is a temperature difference. Similarly, we can say that if there is a difference in the concentration of some chemical species in a mixture, mass transfer will occur. Okay, so basically mass transfer is mass intransient as the result of a species concentration difference is a mixture. So when we have a concentration difference, we have mass transfer. So just look at this this slide. Let's say we have a box. It's divided into two sides, right hand side and left hand side. On the right hand side we have species B, and on the left hand side we have species A. They are just like, let's say they are molecules, for example, BA. Okay, like the chamber is divided into two sections. There is no mass transfer. Why? Because there is no concentration difference. This the right hand side, all the molecules are B, so same concentration. A is the same. So if we remove this basically wall or layer between these two, what will happen is that we are going to have mass transfer from where to where, what side. So it's exactly the same as heat transfer. If you remember, heat was transferring from a surface with a higher temperature to the surface with the lower temperature. The same concept can be applied to mass transfer. So the species, they will transfer from or migrate from area with a higher concentration to the area with lower concentration. We should not confuse it with the bulk fluid motion. Okay, that's like, keep it in mind, because bulk fluid motion occurs on a macroscopic level as a fluid is transferred from one point to another due to difference in the density. But for mass transfer we need two regions with completely different concentrations. Okay, but for, like, let's say when we were talking about natural convection, it was just one species, but it was moving due to difference in density. Okay, now let's just so we just like explained here that the driving force of mass transfer is the concentration difference, and the temperature difference is the driving force of heat transfer. Because it's maybe it's the first time that you are passing a course or any kind of like a study team on mass transfer, we are trying to make it as similar as possible to heat transfer, because you understand the concept of heat transfer properly, I hope, at least. So we are trying to make it similarly to heat transfer, to make it easier for you to understand. That's the reason we are going to talk a lot about the similarity between heat transfer and mass transfer in this study team. Let's like look at some examples here. So we can see that this picture showing, for example, different ways that we are going to have mass transfer. Because in previous slide we talked about gases, so we had two species that they were gases, but mass transfer can also occur in liquids and solids, which we showed some examples in this slide. For example, is like a cup of water left in a room eventually evaporates as a result of the water molecules diffuse into the air. So liquid gas mass transfer. A piece of dry ice or solid carbon dioxide also gets smaller and smaller in time as the carbon dioxide molecules diffuse into the air. So as you can see, the section B, solid to gas mass transfer, very familiar example for all of you. a spoon of sugar in a cup of coffee eventually moves and sweetens the coffee, although the sugar molecules are much heavier than the water molecules, but they disappear inside the liquid. So solid liquid mass transfer as well. The last example is the carbon and iron, the transfer of like solid to solid, which we showed here. But here now we just like talked a little bit, like very simple stuff about the mass transfer. But now we are going to talk a little bit about the analogy between heat and mass transfer. So what are the similarities between them, and after that we just like try to understand. So about the temperature, we just talked about it, that if we want to find a kind of like an analogy between heat transfer and mass transfer, we can say that the driving force of heat transfer is the temperature difference, and the direction of heat, as you can see here, is from a surface or area with higher temperature to the area with a lower temperature. The same mentality applies to mass transfer. The driving force of mass transfer is concentration difference, and when mass transfer happens, it happens like the mass will migrate or transfer from areas with the higher concentration to the areas with the lower concentration. Okay, so that was easy, but I just wanted to mention because we are going just to take one step further. So we talked about temperature, but we know that we have three different like forms of heat transfer. The first one that you learned was conduction, because it's easy. So we talked about conduction heat transfer, but we know that the mass can be transferred by a kind of process similar to conduction. So of course it's not completely exactly the same, but we call it diffusion. Okay, so conduction heat transfer and diffusion, mass diffusion. Okay, so let's try to see if we can find some kind of similarities between conduction heat transfer and mass diffusion. We know that the rate of conduction heat transfer in a direction of x is proportional to the temperature gradient in that direction, and it's expressed by a law that we call it Fourier's law. We mention it here. We call it Fourier's law. Okay, so the conduction heat transfer in a direction of x is proportional to the temperature gradient here, and we mentioned it, Fourier's law. Likewise, as we said, diffusion is the same term for mass conduction, so we can relate mass diffusion m dot diff, which is like an abbreviation for diffusion, mass diffusion, in the direction of x to be somehow proportional to the concentration gradient in x direction. We have it here, concentration gradient in x direction. A surface area will stay the same. If you remember here, we had one constant, which was thermal conductivity. Here we will have another constant, but instead we call it diffusion coefficient. Okay, so we call this correlation Fix Law of Diffusion or Fix Law of Mass Diffusion. It can also we can show like a differential equation for both of them, as well as you can so it's like different forms, but in principle they are the same. So basically what are they is the mass or mass diffusion or mass conduction is one constant multiplied by surface area multiplied by concentration gradient. How about the conduction? Constant multiplied by surface area multiplied by temperature gradient. So it's look like that there is a very good analogy between conduction, heat transfer, and Fourier's law with mass diffusion and Fix Law of Diffusion. Okay, so we talked about conduction. How about convection? So we will speak about all aspects of the analogy between heat and mass convection later, but we should know that the analogy, this analogy that we are talking for convection, is valid for low mass transfer rates cases in which the flow rate of the species undergoing mass flow is low, under 10% relative to the total flow rate of the liquid or gas mixture. But if you look at the correlations, they look more or less the same. We are going to talk about this mass convection and the analogy between mass and heat convection in detail, but just like have it a little bit here, is exactly the same. We have one coefficient in Newton's law of cooling or heat convection. It was here convection heat transfer coefficient multiplied by AS multiplied by temperature difference. The same for m dot convection or mass convection. We will have a coefficient basically multiplied by surface multiplied by concentration difference in this case. Okay. There is another thing that I would like to mention is about the heat generation. We want to see that if there is any kind of like analogy between heat generation terms, because if you remember in heat transfer, when you were like solving some examples, you could see the terms heat generation or internal heat and or something like that. So basically heat generation refers to the conversion of some form of energy such as electrical, chemical or nuclear energy into sensible thermal energy in the medium. So if you remember, a very clear example of it was some kind of we would say that there is like internal heat here, or there is a kind of like an element that creates temperature or some stuff like that. Some mass transfer problems involve chemical reactions, that those chemical reactions occur within the medium and result in the generation of species throughout that box or whatever or environment that we are talking about. Therefore, species generation is a volumetric phenomenon, and the rate of generation may vary from point to point in the medium, so it relates to the location as well. Such reactions that occur within the medium are called homogeneous reactions, okay, homogeneous reaction, and are analogous to the internal heat generation. So homogeneous reactions, we can say that they are exactly like, not exactly, but the concept is very similar to the concept of internal heat generation. But on the other hand, some of the chemical reactions result in the generation of a species at the surface. Okay, so why happens at the surface? Just like due to the contact between the medium and surroundings. So we call it, because it's a surface phenomenon, it's kind of like, you can find a kind of like an analogy between that surface phenomenon and boundary condition. In mass transfer studies, such reactions, we call them heterogeneous reactions, and there are similar to specified surface heat fluxes. Okay. Okay, now we are going to talk about mass diffusion. We just talked a little bit about the mass diffusion and Fix law of diffusion, but here we are going to speak about different ways of showing concentration, basically different languages. There are two different ways of speaking about concentration, or concentration of a species can be expressed in two different ways: mass base or mole base. Considering a small volume of V at location within the mixture, the densities of a species and the mixture at that location are given by these two relations, as you can see. Therefore, the density of a mixture can be written as sum of all the density of all the constituencies or species. There is another concept that we can define here, which is the mass fraction. Mass fraction is a dimensionless number, and because, as you can see, based on the correlation, is like a weight or mass of a species divided by the total mass. So the number is between 0 and 1. It can't be 0, it can't be 1. And yeah, but if we have just one species, yes, but if we have two, it can't be just like 0 or 1. Basically, that's it. It's a very simple way of expressing the concentration. But after that, when we talk about mole base, we can also find some kind of relations between mole base and mass base. For mole base, if we consider a small volume at a location within the mixture, the molar concentrations of a species and of the mixture can be expressed as we mentioned here, like the partial molar concentration of a species I and the total molar concentration of the mixture. There is another concept that can be defined here as a mole fraction. Again, dimensionless number, and that value is between 0 and 1. Okay, now let's to see how those things are related to each other. If you remember what we said, that for mass space, let's go back and see it and write it down here. For mass space, okay, we said that this is, let me just write it down here, it was a mass space. And for mole base or molar base, let's go here and see CINIB. Okay, the volume is the same, am I right? Do you agree with that? So those are the same then. Density, mass, number of moles, concentration. We also know that M, what was M? Do you remember it? Molar weight, yeah, is equal to M divided by N. So basically I can write Mi is equal to Mi divided by Ni. Okay, so let's apply those into each other and see if we can get any sense out of it. So okay, Ci, which is like the concentration, is equal to Mi divided by Ni. On top we have Oi. We just said that it is Mi, so concentration can be as this correlation as well. Very simple. So we mentioned here, but we just showed it. How does it work? But again, we also mentioned that how about the total mass when we are speaking about the total mass, because it said that it's divided by N, am I right, from here, but after that we just like made it I for each species. But we know that in this case it is sigma if we want to write it as a like a sum of the Ni and Mi divided by N. Yeah, do you agree? It's very simple. So it will be sigma Ni and Mi. What is this? Ii. We just like talked about it, which is Y is mole fraction. Let me just write it, mole fraction. But is there any way that we can relate the mole fraction to mass fraction? Yes. Remember the mass fraction is divided by rho. So you agree with that? So what is rho? From we can say that is equal to Yi based on, I'm showing this one, this here, mi divided by m, total mass molar for a species. Okay, so there is a correlation between mole base or mole fraction and mass fraction as well. It's a little bit of manipulating different concept and multiplying, dividing, but just have those correlations that I mentioned here. I try to show a little bit how those correlation came from, but it's not a very complicated story. Okay, now we are going to talk a little bit about the special case of ideal gases. So for example, if a mixture of a dry air, like we have a mixture of dry air and vapor, okay, and that mixture is at atmospheric condition. When we have those mixture of dry air and vapor, which at the same time it's at atmospheric condition, we can treat that mixture as an ideal gas. Okay, so what we can get, okay, what's behind it that we can just consider it as ideal gas, or basically what we are going to receive from considering that mixture as ideal gas. For ideal gas, we know that the pressure is sum of the pressure of the constituencies or different species, which will help a lot in order to find to solve some of the questions later. So the total pressure is basically the sum of the pressure of each species in that environment. So basically that's it. The rest, just please go and read this slide. And now what we are going to talk about is we are going to a little bit talk about the Fix Law of Diffusion a little bit in detail, because first we talked about Fix Law of Diffusion, but after that we talked about different ways of expressing the concentration. So we should talk a little bit about how of those different ways of expressing the condensation will concentration will affect the Fix law, and how the Fix law will look like. I mentioned earlier that the rate of mass diffusion of a species in a medium is in a specified direction is proportional to the local concentration gradient in that direction. Okay, we know it, no problem about it. This linear relationship, we mentioned, that can be written as m dot diffusion. If you remember, we said that dAB A dCA divided by dx. But we know that the concentration of a species in a gas mixture or liquid or solid solution can be defined in several ways. It can, such as density, mass fraction, molar concentration, mole fraction. So Fix law can be expressed mathematically in many different ways. Okay, so now we want just to see how those the different ways look like. So if we want to show the Fix law for mass base, but we want to talk about mass flux. So it's mass flux when we are speaking about the flux, so of course the A will go out of the equation. And if we divide it by A, so this will be how the Fix law will look like when we are speaking about the Fix law mass space. Okay, so basically density DAB d rho A divided by rho dx, and finally for mass space expression we can say that the mass flux is density multiplied by a constant. We know what is the constant. What was the constant? You remember how we called it? What was it? Yes, diffusion coefficient, and it's proportional to gradient of mass fraction. For mole base, it's the same, but concentration multiplied by diffusion coefficient, and it's proportional to the gradient of mole fraction. For mass space is if the density is constant, so of course the mass flux can be written differently, the same as molar base when the concentration is constant. Okay? But there are other ways of, like, because you might see the some kind of questions that they don't say directly that the density is constant, but that constant density or molar concentration assumption is usually appropriate for solids or dilute liquid solutions, but often this is not the case for gas mixture or concentrated liquid solutions. So for example, if I say that solid, so it is a very good engineering assumption to say that, okay, density or molar concentration are constant, the same as if we are talking about dilute liquid solution. But when I'm talking about gases and different gas species or concentrated liquid solutions, this assumption of constant density or molar concentration actually is not a very good assumption. Besides that, we should know that the relationship that we mentioned here for all of them are for one-dimensional mass diffusion. For 2 or 3-dimensional cases, Fix law can be expressed differently. You remember, it's like conduction. We were just like talking first one direction. The same, we start talking about one-dimensional or one-direction mass diffusion, but for 2 or 3-dimensional cases, basically what we have is JA. Basically, I'm just like going to write for mass space density, diffusion coefficient, UA. It's for 2 or 3-dimensional cases. You remember that, again, we mentioned mass diffusion is similar to conduction heat transfer. and you remember that we call the constant in Fourier's law thermal conductivity. Now we have to define this constant, because we said that it is the diffusion coefficient, but how we are going to calculate it and things related to that. Because there is a way, if you remember, for thermal conductivity, we have a kind of table at the end of the textbook that you can go and find the thermal conductivity of normal liquid or solids that we use, so no problem, it's just a constant. But how about this DAB? This constant is called binary diffusion coefficient. It's also called mass diffusivity. So all of them, they are talking about the same thing. So diffusion coefficient, mass diffusion coefficient, binary diffusion coefficient, or mass diffusivity. Okay, now we talked about it, how we call it, but what about the unit? Because it's very important to have it. So DAB, the unit is per second, square meter per second. So square meter per second does ring a bell. Is it similar to any other units that we faced during the last time that we were talking about heat transfer? If you think this unit, which is square meter per second, is the same as kinematic viscosity, which is the momentum diffusivity. You remember that? If you go to the table, you can find that unit. So due to complicated nature of mass diffusion, the diffusion coefficients are usually determined experimentally. So now when we talked about it, when we realized what unit we are talking, now it's time to see how we can determine them. So as I mentioned, they are complicated, usually determined experimentally. But from kinetic theory of gases, we have these two correlations. So DAB is related to temperature to power of 3 divided by 2 divided by pressure, and here it's very important how this binary diffusion coefficient or mass diffusivity or diffusion coefficient is related to the pressure and temperature of species. So if we have the diffusion coefficient of a gas at a specified temperature and pressure, so easily we can find the diffusion coefficient for the rest of temperatures and pressures. So we don't need to have all. By this correlation, if we have the diffusion coefficient for a specific gas for a specific temperature and pressure, we can have the other a diffusion coefficient at different temperatures or pressures. The binary diffusion coefficients for several gas mixtures, solids and liquid solutions are given in table 14.2 and 14.3 of the textbook. Let me show it here to you. So if there is any kind of a question asking something that you need to find the diffusion coefficient or binary diffusion coefficient, so you know where you need to look for it. Okay, so is there any other like a kind of no, I think we just like mentioned everything here. Okay, so okay, but here let me just like give you a little bit of information here about this, because so for example, when we are talking about T, so temperature, if you remember, we had the same story in radiation as well. What temperature, like should you put the temperature as a centigrade or Kelvin, or how does it work? Here you need to keep in mind that the temperature should be in Kelvin, and this pressure is total pressure. Okay, so that's for clarification. I think that's it for this this section. Let's just like let's solve some very simple examples, or try to answer some questions to see if we really understand the concept of this lecture properly. So we start first with 14.15. So it's asking us to answer the question. The information is as there, like the composition of moist air is given on a molar base to be 78% nitrogen, 20% oxygen, and 2% water vapor. Determine the mass fraction of the constituencies of air. Okay, how we are going to calculate that? Let's just like open a page. So what is asking is like mass fraction of, is asking for mass fraction. So we know that for mass fraction, let's say we need to have the mass divided the mass total, basically. Okay, we also said that the mass fraction is equal to molar fraction divided by, multiplied by mi divided by total. Okay, so we have this stuff. We know that molar weight of oxygen molar weight of water, molar weight of nitrogen. We know it, or if we can't remember, we can go to table and read them. 18, and this one is 32. Okay, so first we need to find the total mass. So the total mass is equal to YIMI, so it will be 0.78 multiplied by 28 plus 0.2 multiplied by 32 plus 0.02 multiplied by 18, which is 28.6 kilogram per kilomole. Okay, so now if we want to find the mass fraction of, let's say, nitrogen. So the mass fraction of nitrogen, I can write it like that, is equal to divided by m. Let me just write the units are important, should never forget that. So we have this one 0.78, we have the total 8.6 kilogram per kilomole, we have this nitrogen 28 kilogram per kilomole, so M2 is equal to 0.764. The mass fraction of oxygen is equal to 0.224, and mass fraction of H2O is equal to 0.012. Okay, so try to do it yourself and see if you can get the same results. So you see that the results are mentioned here. The second one is saying that the molar analysis of a gas mixture at 290 Kelvin and 250 kilopascal is 65% nitrogen, 20% oxygen, 15% carbon dioxide. Determine the mass fraction and partial pressure of each gas. So it's like, it's again asking for mass fraction, but on top of that is asking for partial pressure of each gas as well. So let's see if we can solve it. So again, we said that we know that the mass fraction is equal to molar fraction I m total. We just like mentioned m here. So, and we said that total is yi mi. So we can calculate all of that because we have the y's and we have the m, because we can read it from the table. So basically is 0.65 multiplied by 28 plus 0.2 multiplied by 32 plus 0.15 multiplied by 44 is equal to 31.2 kilogram kilomole. Okay, so I'm not just going to write all those correlations, but I'm just going to write the final answer, 0.583. Mass fraction of oxygen is 0.205, and mass fraction of carbon dioxide is going to be 0.212. But it's asking to find the pressure as well. Am I right? Let's go back and check. Yeah, the partial pressure of each gas. Note that the total pressure of the mixture is given. Yeah, the total pressure P is given to be 250 kilopascal. And the pressure fraction in an ideal gas, if you remember, we mentioned that the P in ideal gas is sum of the is equal to the partial pressure of the individual gas. But it's like, how does it work? Is it like because if you remember here, there is like something is missing here. So pressure, if I just like put a pressure, for example, like how I can say that what is the pressure of each of those basically constituencies or species. So here we need to know that for P, basically the total pressure, but it's when we are speaking about the ideal gas, is equal to Like let's say for example species I is yi p, total p. Okay, for example, let's apply it here. For example, if I want to find the pressure of nitrogen, so it's y nitrogen multiplied by total pressure, so it will be equal to 0.65 multiplied by 250 kilopascal, which will be 162.5 kilopascal. The same way we can calculate it for the partial pressure of oxygen and partial pressure of carbon dioxide. Basically that's it. So please try to go through the rest of questions and see if you can solve them. That was the end of our lecture today, and see you next time.